Good day, my name is Glenn Nice and I'm with the Pesticide Applicators Training Program at the UW, and today I'm going to talk about everyone's favorite subject, calibration. Why do we calibrate? Well, we calibrate to make sure that we are applying the correct amount of pesticide. You don't want to apply too much and injure the crops you are trying to protect and possibly cause environmental issues. And you don't want to apply not enough, because in that case you may not actually do the job and the tool may not do the job that is required. We also want to calibrate because we want to be safe. You are producing crops that people eat, and these crops can have certain amounts of pesticide residues on them after using pesticides. Well, we want to make sure that we apply the correct amount of pesticide to assure that the time between application and the time between harvest and selling to your customers doesn't cause any health issues. When you apply a pesticide, what happens to it? Does it just disappear? Does it just disappear? Or does it take time for that pesticide to break down? In truth, it takes time for that pesticide to break down. And in this slide, I show several things. I show a time frame from 1 day to 24 days. And then I also show that when we sprayed, and I used a ginseng plant there in case anybody's a ginseng producer, you spray onto this ginseng plant and it takes time for that pesticide to break down. All pesticides break down, but they will break down at different times, or it will take different times for them to actually break down into smaller components. So for instance, we sprayed a pesticide. Within 1 day, let's say we have 100 parts per million still on that plant. Well, at the end of 3 days, we have 50 parts per million. That is called a half-life. As a pesticide breaks down, a half-life is the number of days or the period of time that that pesticide is broken down to half. So 50 parts per million. After 6 days, we have 25 parts per million. And after 12 days, we have 12 parts per million. So notice how this pesticide is breaking down over a 12-day period. And then after 24 days, we find that it is broken down enough, 6 parts per million, that it is deemed safe to eat. Now, if you put out too much pesticide, just imagine this process will take longer. And if you put out too much pesticide, when it reaches 24 days, and when you can harvest and sell your vegetables, you may have an illegal residue of pesticide on those vegetables. And that's very bad, because the EPA sets certain limits, certain tolerances for how much pesticide can be on that crop when you take it to market. And if there's too much pesticide on that crop, then it is deemed illegal because it is a health issue. So let's take a look at one of the pesticides you may use, 7. The EPA has set tolerances for 7 on various crops. And I've got here cabbage, sweet corn, lettuce, peas and beans, and vegetables, brassica, which is your lettuce vegetables. Notice that the amount tolerated on those foods of 7 in parts per million is 21. Sweet corn is 0.1. Not much tolerance of the stuff of 7 being on sweet corn when you sell it. Lettuce is 10 parts per million. Peas and beans are 22 parts per million. And vegetables, brassicas, 10 parts per million. Why am I showing you this? I'm just letting you know that there are certain tolerances or certain levels that are tolerated of residues of specific pesticides on certain crops. Why else do we calibrate? Well, we also calibrate to make sure that we do not injure our crops. You're spending money and applying pesticides to protect those crops. Why would we want to injure them by putting too much out? At certain levels, some pesticides can literally cause damage. Also, we want to calibrate our equipment to make sure we're not wasting money. Why would you want to waste money on a pesticide that's not working? And a part of that is making sure that we are putting out the exact amount that the label says we have to be putting out. We also want to calibrate our equipment because, well, the truth is, it's the law. The law requires that your pesticide equipment be calibrated and you have an understanding and a knowledge of how much pesticide and being able to control how much pesticide you're putting out. It's very important. Okay, well, that's why we calibrate. But let's look at a sprayer. And this is a very simple diagram of just about every hydraulic sprayer you will ever use. A sprayer has a tank. That's where you put the water, and that's where you put the pesticide. All sprayers have a pump. And all sprayers have a mechanism for delivery. You deliver the pesticide. And this is often, most often than not, a nozzle of some sort. Well, this is a simple diagram of just about every sprayer you'll come across. For instance, this one. Here's your tank, there's your pump, and there's your nozzle. It controls how much is being put out. What about this one? This one's probably one you use all the time. There's your tank, there's your pump, and of course, there's your nozzle. And even this one has the same mechanisms as the one you saw just before it. There's your tank, there's your pump, and there's your nozzles controlling how much pesticide is being put out and what pattern it's being put out. So all hydraulic sprayers are the same. They all have these very similar components. No matter how special they get, this one might have a nice CD player, whereas the backpack one doesn't. That's the only big difference. And the price tag might be quite a bit different too. So what influences what comes out that nozzle? Well, the first thing that influences what comes out that nozzle is pressure. When you're using a backpack with a hand pump, you're pumping that backpack and that pressure is building. So pressure is the amount of force that we're forcing that liquid through that tiny little hole, that nozzle. There's a problem with pressure though. Pressure is not a good mechanism to change large outputs of your sprayer. Reason for that is pressure works on a 1:4 ratio. You have to increase pressure 4 times to increase output by 1. Now the problem with that is if you increase pressure way too much, guess what happens? You may drift. And if you injure your neighbor's crop or you injure plants on your neighbor's field or you drift onto a neighbor's property, that could get you in a lot of trouble. So here's an example. In this example, I have 2 pressures and 2 outputs. This pressure is 10 pounds per square inch, and I'm putting out 10 gallons per acre. Notice I have to go up to 40 pounds per square inch, a ×4 rate of pressure, to double what I'm putting out at 20 gallons per acre. Possibly at that pressure I may start to see drift, so it's not a good idea to crank up pressure to change output by too much. A simpler and better way of doing it is possibly changing the nozzle you're using. Nozzles can put out several types of patterns, and each nozzle, a company that makes nozzles, will rate them to gallons per acre at a certain pressure. But a lot of nozzles put out a cone, or they may put out a flat pattern like so. But keep in mind that the nozzle you have will put out a certain amount of liquid over a certain amount of area. It's very important to know that. This particular nozzle right here puts out 1 gallon per minute. So you know at a certain pressure that nozzle is putting out 1 gallon of liquid per minute. Now, of course, look at the size of this hole here. This is the size of your nozzle. Well, if your nozzle gets a larger hole, what's it going to do? Put out more or less per minute? Well, it's going to put out more, of course. So this nozzle puts out 5 gallons per minute at the same pressure. So using your nozzle is one way you can change the output that you're putting out. Another way you can change output, and maybe the simplest way to change output, is simply by changing your speed. So here I have my old grad student here. She's putting out some pesticide with a backpack sprayer, and she's walking at 3 miles an hour. What if she slows down? Here she is walking at 3 miles an hour, spraying some ginseng. Here she is walking at 1.5 miles per hour, spraying some ginseng. Who put out more and who put out less? Well, increasing the speed, you apply at a decreased amount. So essentially, going 1.5 miles per hour, you might be putting out at 10 gallons per acre. If you increase speed to 3 miles per hour, then you put out at 5 gallons per acre. So, faster you go, the less you put out. Slower you go, the more you put out. And it's also important to understand pattern. Some people may apply pesticides in one linear row. For example, if you're applying to ginseng, you might apply in one linear row. However, if you're doing a broadcast application, you might apply like a pendulum. Spray in a pendulum fashion, having a wider output. So, what's important is you keep the same method of application that you use when you calibrate. That's very important. Okay, so now we sort of talked about that a little bit. Now, why do we all do this? Well, we do this to find out how much pesticide we're going to be putting in the tank. We have to know this, and there are several different things we have to know about this. The first thing is, rates are given in many different ways. A pesticide can give you a rate in a way that is per gallon. For instance, 4 pints per gallon. Or it could be a percentage. Or it could be over a certain area. At this, I just want to sort of point out some of the differences in size. It's very important that you understand that there are 4 quarts in a gallon, there are 8 pints in a gallon, and there are 128 fluid ounces in a gallon. And these are all measurements that you will come across while calibrating your backpack or your spray application rig or your equipment. Rates can be given in several different ways. One possible way is it's given as a percentage. And this is a type of rate that's often used in spot treatments. And an example of these are pints per 100 gallons, or 1.5% volume to volume. The important thing about these types of rates is it's not very important what's coming out the nozzle as long as your technique is good. Meaning when you're spraying, you get a nice coverage, like so, but you do not get runoff. Labels that give you a percentage rate will always say, apply for good coverage, but not to runoff. If it starts to drip too much, you're putting out too much. So it's important that you don't drip, and your technique is important in this case. Let's do an example of this. Okay, you have a rate of a pesticide, let's say a fungicide, and the rate is 2 pints per 100 gallons. Okay? Well, the important part about this is, let's find out how much pesticide per gallon we are putting out at. For example, we have 2 pints, we divide it by 100 gallons, that's what the rate asks for, and we find out that in each gallon, 0.02 pints per gallon. That is our pesticide rate per gallon. Well, we've got a 4-gallon backpack and we're ready to go out there and spray, so how much pesticide needs to go in that? We take our gallons we're going to mix up and we times it by 0.02, the rate per gallon, and we find we need to put 0.08 pints in the backpack. So again, the important part about this is you're applying to good coverage, but not to run off. So we want to apply that pesticide that gets really good coverage, but we don't want it to form drops and start to drop off the plant itself. Well, 0.08 pints, that's kind of a hard thing to measure out. And probably you don't have a measuring device that would do that well. So let's turn that into fluid ounces. Well, 0.08 pints times 16. There are 16 fluid ounces in each pint. Works out to 1.28 fluid ounces. Now that might be something we can measure. We may have an ounce measuring cylinder, or we may be using a syringe with ounces on it, or something to that effect. Okay, this is another percent rate. This is a 1.5% volume to volume. How do we work that out? How do we know what goes in the tank with that? Well, we take 1.5%, divide it by 100, and that gives us how much we have to multiply to find out what volume we want to apply. And that works out to 0.015. All right? 0.015, we still have the same tank we're spraying with. It's a 4-gallon tank. Turns out, well, we have to put in 0.06 gallons of pesticide in each 4-gallon tank. Well, again, that's hard to measure, 0.06 gallons. We don't have something that can measure that well. So we turn it into fluid ounces again. 0.06 times 128 equals 7.7 fluid ounces. We can measure that. Okay, at this point, I'm going to transition from percent rates to rates over an area. So keep that in mind. Now we're moving into a different type of rate. And a rate per area means that is how much of our spray mix and pesticide is going to go out in a specific defined area. For instance, here's an example. 2 pints per acre. That means in this acre, I have to make sure that I'm calibrated that only 2 pints of that pesticide is going to go out in that acre. Well, here we have a problem. Now we can't just apply for good coverage, but not to runoff. Now we have to know exactly what we're putting out at. So what's coming out this nozzle is now very important to make sure we're delivering the correct rate of pesticide. How do we do that? Well, we take an area, a very well-defined area. In this case, 250 square feet. Well, how do we measure out 250 square feet? Well, it could be 10 feet by 25 feet, because length times height is square feet. So 25 times 10 is 250, and we've got our measured, we have a defined area. Now what you also can do is if you are putting out at a foot width, you could literally go 1 foot divided by 250 square feet would give you how far you have to walk to put out at a 250 square feet. For instance, you would have to go 250 feet with a 1 foot wide application, and you would have 250 square feet. Okay, so why are we doing this? We're set in a very defined area, and we're literally going to apply it to that area to find out what we're putting out. So take your backpack, find a nice area. You can use a Sharpie, or you can find a line on your backpack and fill it up to this line. And then go to your test area and spray it. Make sure you get good coverage, just like you would over the ginseng or over your vegetables or over whatever it is you're spraying. Make sure you spray this whole area and use the technique you have for your spraying. It's very important. All right, I've sprayed the area. I can take my backpack off, and I'm going to fill that back up to that line. And the amount I put into that, filling it back up, is the amount I used in 250 square feet. Pretty straightforward. Pretty straightforward. You now know how much you're putting out. For my example, I've picked 110 fluid ounces. That's how much I put out in 250 square feet. Okay? So you put out 110 fluid ounces per 250 square feet. That was your test area. Well, what's 250 square feet to 1,000? That's a quarter of 1,000 square feet. Correct? Well, 110 fluid ounces times 4. I now know the fluid ounces I put out in 1,000 square feet. Pretty straightforward. But if I want to know how many gallons I put out in 1,000 square feet. Well, to change fluid ounces to gallons, I divide it by 128, because there are 128 fluid ounces in a gallon. Turns out, in 1,000 square feet, an area of 1,000 square feet, I put out 3.4 gallons. Well, now I know what I'm putting out. Well, what is that per acre? Well, 1,000 square feet, that's not an acre, but I need to know how much I'm putting out per acre. 3.4 gallons per 1,000 square feet times 43.56. How many square feet are in an acre? 43,560 square feet in an acre. But I know how much I'm putting out in 1,000, so it's 43.56. Turns out, with my technique, when I sprayed my test area, I put out 148 gallons per acre. Now I know how much I'm putting out in 1 acre. Okay? So, my rate, remember, is 2 pints of pesticide per acre. Well, 2 pints divided by the amount of liquid I'm putting out in an acre, 148 gallons per acre, works out to 0.01 pints per gallon. So now I know with my technique what my backpack is putting out. I can now know that 0.01 pints goes into every gallon I mix in my backpack. 0.01 gallons times 16, that's, oh, I apologize, 0.01 pints per gallon times 16 equals 0.16 fluid ounces per gallon. I can work with that. That's a small amount per gallon, but just remember how much liquid you're putting out. So you really don't have to put that much in there to get that much out. So we determined that 0.16 fluid ounces per gallon. So 4 gallons times 1.6 fluid ounces equals 0.64 fluid ounces per tank. Well, thank you for listening to my presentation today, and I hope that this will help in your practices in the field.